mind. Come on. You silly head. So silly. Mind. Yeah. Alright, we got redox on the agenda, but we got to wrap up organic reactions. And by wrap up, I mean start and finish, because I didn't get there yesterday. So, let's get going. So, we're going to wrap up organic from yesterday. Most of organic chemistry we covered. I kind of hate the reflection in the glasses sometimes. Hey. Most of organic we covered in yesterday. So, we just have to do the reactions, which is the hardest part about organic because it's not on the reference table anywhere. So, keep in mind these are organic reactions because they all are reactions involving the element carbon. So, first one's addition. If you take an alkene and add typically something from group 17, you'll notice it will be just directly added to the compound. So it's alkenes only. How do you know if you have an alkene? Check the formula and put it into all the formulas on table Q and see which one pops out as correct. Since I have exactly double the amount of hydrogens that I do carbons, that's the general formula for an alkene. So, reactions will occur in alkenes only, or I guess alkynes, something that has a double or triple bond only. So alkenes and kynes. And that's because if we draw out this carbon compound, we got to keep in mind carbon wants 4 bonds. So these two chlorines can come in and take these bonds away from carbon and bond to the carbon in its place. Or, yeah, in place of the double bond. So addition reactions is a hydrocarbon that's an alkene or an alkyne plus usually something from group 17 literally being added to that compound. Versus substitution is going to occur with alkanes only. And that's because alkanes have single bonds. So you can't fit anything else on those carbons because carbon only wants 4 bonds. And since all those carbons are occupied with bonds, if we added something from group 17 to this compound, it wouldn't actually be added. One of them is going to do a trade with one of the hydrogens. Like you're substituting a player. In a sports, you go out, the other player comes in. Or you go in, and your teammate comes out of the game. So that's HBr. And a lot of these substitution and addition reactions, not only do you just need to know they're organic reactions, but you just need to be able to recognize. If you see a picture of this reaction occurring, you need to be able to say, that's substitution. Or if it's condensed, like C3H8 plus, let's do F2, you'll get C3H7F plus HF. Something along those lines. Something where they're not being added to the compound, they're being substituted in. Or maybe both F's will get added to this compound here, and the H2 pops out. Something where there's a switch, not an addition. I'm going to save the hardest ones for last. Combustion. Combustion is any hydrocarbon, so any CH compound, I'm just going to abbreviate it CXHY, plus oxygen will always result in the same products, carbon dioxide and water. Combustion always makes the same products. You take a hydrocarbon, add oxygen, what do you make? Carbon dioxide and water every single time. Saponification is really complicated. And the biggest thing about saponification is it makes soap. The reaction involves a base, but everything else is really complicated. So usually, I would just say fat plus base, like NaOH, makes soap. That's about the extent I would get in depth with saponification here. Actually, I'm going to save that one for a minute. Let's do polymerization. So polymerization is many things, which you might remember the word from bio called monomer. So many monomers make one big thing. And that big thing is typically called a polymer. Like polyester. Polymer, polymer. So, how do you see this reaction? I've seen it two ways. You see like this dot, 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 implying that there's a bunch of them coming together. Dot, 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 making one huge CH2 molecule, maybe with an N down here. A lot of the ones with polymerization, you'll see these N's. So, sometimes instead of doing the dot, dot, dots, they'll just use N's. So, like, these N amounts of CH2s being added will just make one giant CH2 molecule. They always use N for some reason. I don't know why. But the basic principle of it is numerous little things become one gigantic thing. So it's not addition. Addition was just like adding a couple of atoms to a basic hydrocarbon. And it's always an alkene or alkyne. While polymerization is taking a whole bunch of small things and just throwing them all together. So, that's polymerization. Fermentation. The one, at least when my kiddos took this test, that one proved to be the most difficult one. So, fermentation is the same reaction every time. You take some sugar, like glucose, and you react it with some enzyme, usually found in yeast. You will always get an alcohol and carbon dioxide every single time. So if you've ever made bread dough at home, you need yeast, sugar, water. You get some like lukewarm water, put yeast in it with some sugar, and you let it ferment over time. And when you start making the dough will start to rise. And that rising is because of the CO2 being formed. And then before you actually like mix making a dough, the alcohol, you can smell that. Because this reaction is also used to make certain types of alcoholic beverages. So, that's fermentation. Sugar makes alcohol and carbon dioxide. It's the hardest one to recognize. If it's a chemical formula, and I probably won't balance this equation, but you just need an alcohol and carbon dioxide. Just as soon as you see sugar as your reactant, and it's not photosynthesis, photosynthesis, that would be a product. If it's not respiration, which you probably won't see because this isn't bio, it's fermentation. All right, esterification is the most complicated one. And esterification will always be an organic acid plus an alcohol make an ester plus water. So what does that look like? Let's show. So an organic acid can look something like this. And an alcohol can look, I'm going to draw it backwards, something like this. Remember, these lines are just representing hydrogens. So they react, what do they make? These right here are going to form your water molecule. So that within the box makes your water. And then this oxygen is now lonely. And this carbon is now lonely. And the carbon's going to come in and attach itself to the oxygen. And when you do that, your product is going to end up looking like this. And this formula right here, when you see this being sandwiched in the middle, that is an ester. So when you check table R and you see the generic formula, and you notice that in your compound, that's your ester. So this is esterification. So the normal ways you can spot it is if they give you the whole reaction and you see an ester being made, that's esterification. All right, let's do redox. Those are the organic. There will be plenty of practice on this on my teacher site for you to look over. Okay? So, redox. Let's start with oxidation numbers. So, redox is an abbreviation for oxidation and reduction. Or I guess in this case, reduction and oxidation. The first basic thing you need to be able to do is give yourself a formula, or if given a formula, you need to be able to tell me, or whoever, what the oxidation number of each of those individual atoms are in that formula. And that's the key word. I don't want you to tell me what O4 is at the end. I need you to tell me what O is. So all the charges, all those pluses and minus need to equal 0. And if they don't equal 0, it's not balanced. So, let's go to the periodic table and see which ones we can get. K is +1. That only one charge. That's nice. Mn's a pain in the butt, so we'll keep that in mind. And O only has one charge. Well, that's nice too. So, K is always +1, and O is always -2. So I figured those out already. Now I just need to figure out the Mn. So I know K is going to be +1. I know oxygen's -2, but there's 4 of them. So each oxygen is charged -2. So since there's 4, the overall is going to be -8. And I need these all to add up to be 0. I need this 1 plus something -8 to equal 0. Well, if you check Mn's charges, your only options were 2, 3, 5, and 7. And doing a quick little math in my head, if I put in a 7 here for x, 1 plus 7 is 8. 8 minus 8 is 0. 7. Let's do another one. Let's do calcium carbonate. CaCO. Okay, so you would check the periodic table in this instance. I know calcium's a group 2 element, so that's always +2. We just did oxygen. That's always -2. So my calcium is +2. My oxygen is -2, but there are 3 of them to make -6. So I have 2 plus something -6 equals 0. What could x be? Well, again, doing some math in my head, 2 plus 4 is 6, and 6 minus 6 is 0. So my x, my carbon, must be charged +4. You also should be able to, given a chemical reaction, figure out the oxidation states of all those elements. So let's say you had H2 plus O2 combining together to make H2O. First important point, when an atom is bonded to itself and nobody else, if it's only bonded to itself or only exists by itself, so for example, if we had one that was like Mg plus HCl makes MgCl2 plus H2. If it only exists by itself, or it's only bonded to itself, the charge on all of them is always 0. So when an atom is alone, or only bonded, its charge is 0. So, oxygen here, so what's the H on this side? What's the O? O is always -2. I have 2 hydrogens though. So what -2 is 0? Well, I know 2 minus 2 is 0, but since I already have 2 hydrogens, these must just each be charged plus 1. 2 times 1 is 2. 2 minus 2 is 0. Here, chlorine ends up being more electronegative than hydrogen. And generally speaking, if you have a compound, the second one is always the negative one. So I know chlorine's -1 and hydrogen's +1. Here, I know chlorine is still -1 for a total charge of -2. Magnesium is +2. So you also need to be able to just look at a reaction, pick the ones that are alone, and say those are 0 in terms of their oxidation state or charge, and then look at the ones in the bond and just do exactly what you did up here. Write down all your atoms, get the oxidation states from the periodic table. If it has multiple oxidation states, save that one for last. Okay. How can you tell if you have a redox reaction? So generally speaking, how do you know if you have a redox reaction? Reduction / oxidation is even occurring. Well, if you look at it, a single replacement is always redox. But what if you don't remember that? Well, you have to look at each reaction, and if the atoms change charge, so if they went from 0 to -2, +1 to 0, -2 to -3, whatever, it doesn't matter. If they change charge from left to right, that's redox. So the 2 reactions I just did are called redox reactions because the hydrogen 0 to +1. The oxygens went from 0 to -2. Since the charge changed on both sides, we have a redox reaction. Same thing with this second one. This second one, first of all, is single replacement. So these two switched with each other, the H's and the Mg's. But if you didn't remember that, if you check their charges, you will again notice that they have changed. And if you have a change in charge, then you have a redox reaction. What is oxidation and reduction? Reduction equals charge goes down. So, an example would be Mg. Actually, I don't want to do Mg. I just did Mg. Let's do zinc. Zn plus 2 going to Zn with a charge of 0. If you see that charge getting smaller, you have a reduction occurring. How do you know or what does that mean? Why does the charge go down? So here comes acronym number 1. Gain electrons reduction. I just ran out of room, but you heard me say it. Gain electrons reduction. For zinc to go from +2 to 0, its charge has gotten smaller, therefore it's getting reduced, and it has gained electrons. So you would show this half reaction as Zn2+, gaining 2 electrons to become Zn0. Whoa, 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 whoa. Let me make my Z's with these dashes so you can tell they're Z's and not 2's. Hold on. Why? How does the charge get smaller if you're gaining something? You're not making any sense. Well, what's the charge of an electron? -1. And if you're gaining negatives, that means your charge is going to get smaller. Oxidation is the opposite. Oxidation, the charge increases. So, that would be like, let's do calcium. Going from 0 to calcium +2. Why does that happen? Now, here comes the second acronym. Lose electrons oxidation. Lose electrons oxidation, gain electrons reduction. Leo says grr. Lose electrons oxidation, gain electrons reduction. Lose electrons oxidation, gain electrons reduction. So, how can you show electrons being lost? Well, take your calcium charge 0 and show it losing 2 electrons by showing it on the right-hand side of your chemical reaction. Wait a minute. Why are you saying +2E negative if they're being lost? Well, the right side of the chemical reaction typically means things are being produced. And in this case, since you're producing 2 electrons, that means those electrons have left calcium and gone into zinc. So, to show electrons being lost, you write +2E minus on the right-hand side of the reaction. A chemical reaction, any chemical reaction, never uses subtraction. So don't do it. Okay, now, when you have a chemical, you must always conserve the following: mass, energy, charge. What the heck does that mean to conserve that? I don't understand. So, if you conserve mass, that means the mass in equals the mass out. Okay? Same thing with charge. The charge in has to equal the charge out. Same with energy. You cannot create or destroy mass. You cannot create or destroy energy. You cannot create or destroy charge. What goes in needs to be what goes out. Everything is conserved. And these are for chemical reactions, okay? Energy and mass get a little complicated, especially energy, when you start dealing with nuclear reactions, which we'll talk about tomorrow. But if it's a chemical reaction, you conserve mass, charge, and energy. Let's look at a voltaic cell. So typically, aside from that 1 year, they decided to get a little complicated and gave you a potato. Your voltaic cell is going to look like this, where that's your salt bridge. We got our wire, Now I'm going to pick 2 random electrodes. Let's do a magnesium electrode and a lead electrode. First, if a chemical reaction wasn't given, and it almost always will, because they have to give you the charges of these things, how do you know who would be oxidized and who would be reduced? If you check table J, and we're going to compare Mg and Pb. So Mg is here, and Pb is here. So whoever is above will get oxidized, and whoever is below will be reduced. And if you connect these 2 things, if you connect together with a wire and that salt bridge and put them in some solution, Mg and Pb, this would be a spontaneous reaction. Since Mg is above Pb, you don't have to do anything. Since Mg is being oxidized, the electrons are just going to leave Mg and move into the electrode of Pb. So, how do you know if a reaction is spontaneous? A voltaic cell, so a voltaic cell which looks like this. Voltaic is always spontaneous. A voltaic cell makes electrical energy. And a voltaic cell will always be some sort of oxidation and reduction reaction. So if you see a voltaic cell like this, when you look at it, there won't be a battery. No battery. That means this reaction is spontaneous. As soon as you connect Mg and Pb, Mg will be oxidized since it's above Pb on table J. So Mg will be oxidized, and Pb, since it's lower, since it's going down table J, gets reduced. As soon as you connect these 2 things, you're going to start producing electrical energy. And since you don't do anything, meaning you don't input any energy for this to occur, as soon as you connect them together like this, they will generate that power. We call that spontaneous. So all voltaic cells are electrical energy producing spontaneous chemical reactions. So keep in mind that this is spontaneous chemical reaction, because these are chemicals reacting with each other to form something new. But more often than not, you will see a chemical equation. And it's going to look something like AQ plus Mg as a solid makes Pb AQ and Mg as a charged ion. Okay, how many different questions can they possibly ask about this? A lot. First, the wire contains electrons. The electrons are flowing through the wire. Kanye West. The salt bridge has ions, and the ions are there to help maintain like sort of electrical equilibrium, just to make sure this reaction proceeds normally and doesn't get out of whack. Okay? So, that's one thing they could ask. They could ask you to show the half reactions for who's getting oxidized and or reduced. So if they ask you for the half reactions, you could, 1, check table J to see who's getting reduced, which we already did. It's lead. Or 2, just look at the charges. So since lead, I didn't want to do that. Since lead is plus 4 here and 0 here because it's alone, lead's charge went down. Lead's charge got reduced. So if they ask you to show the reduction half reaction, that means lead, with its 4+ charge, has gained 4 electrons to make lead with no charge. If they were to ask you to say who was oxidized, show the half reaction for the oxidation, that would be the opposite. So Mg went from a solid atom with no charge to an aqueous ion with a charge of 2, meaning it must have lost 2 electrons. They will also ask you about how many electrons has been lost or gained in these chemical reactions. Well, the electrons going into lead have to be the same as the electrons flowing out of magnesium. And since this is a 4 and this is a 2, those are not the same. So, how can we make them both the same? Usually, an easy way is to take the electrons on the bottom and multiply that into the top reaction, and take the electrons over here and multiply that into the bottom reaction. But I think just if I multiply this times 2, that will make those electrons 4, and then these will cancel out. So if I multiply that times 2, you'll get 2Mg, make 2Mg aqueous plus 4 electrons. All I did was distribute that 2. Now these cancel out, and when you combine them for the full reaction, you have Pb4 plus 2Mg0 make Pb plus 2Mg2 plus. And that's aqueous, solid, solid, aqueous. Where are the electrons flowing? So what if there's a question on electron flow? You're going to sit there and go, wait, are they going from Mg to Pb? Are they flowing from Pb to Mg? They're flowing from anode to cathode. The electrons always flow from anode to cathode. Just say that. What if there's other questions about anode and cathode? There's an acronym for this. The anode is where oxidation occurs, and the cathode is where reduction occurs. Red, cat, and ox. Reduction is cathode. Anode is oxidation. They could ask, who's gaining or losing mass? And typically, they want you to describe this in terms of atoms and ions. And that's easier than you think. If you just look at the chemical equation and tell me who went from an atom to an ion, and who went from an ion to an atom, you can answer this question. So, generally speaking, who's gaining is always going to be the cathode, not because it's gaining electrons, and who's losing mass is usually going to be the anode. And again, not because of the electrons. Electrons essentially weigh nothing. The electrons are causing something else to happen, but that's not happening because it's gaining electrons. If you look at the reaction that I gave you at the beginning, and now we balanced it, 2, lead goes from a charge +4 to a no charge of 0. +4 is an ion. 0 is an atom. Lead changed from an ion to an atom. Versus Mg went from a no charge of 0, no charge is an atom, to plus Mg is an ion. Mg changed from an atom to an ion. So who gained? Well, the gain, Pb, because it changed from an atom, it changed from an ion into an atom. And who lost? Well, Mg, because that went from an atom to an ion. And a lot of times they'll give you a hint in the question, like, explain in terms of atoms and ions why Mg is losing mass. Well, it changed from an atom to an ion. The end. All right, so that's pretty much all they can ask with these voltaic cells. Always remember anode to cathode for the direction of the electron flow. Let's see. I did red cat anox. Wire is electrons. Salt bridge is ions. All right, what about an electrolytic cell? An electrolytic cell uses similar principles but flips it a little bit on its head. So electrolytic are not spontaneous. Electrolytic require a power source. Electrolytic is going to flip table J. Electrolytic creates chemical energy. So, basically what you're doing, when you normally connect, let's use Pb and Mg again. When you normally connect Pb and Mg together through that wire, normally the electrons are going to leave Mg and go to Pb. That's the natural, spontaneous, easy way. However, if you were to attach a power source, like a battery, to that reaction, you can cause the reaction to go in reverse. And since you needed this power source here, since you needed something like a battery, you flipped table J. You are now causing Pb to lose electrons and send them to Mg. You are oxidizing Pb when Pb wants to be reduced. And since you're doing this using electricity, what you're creating is chemical energy. A voltaic cell, like this, since that is connected without an outside energy source, it will follow the principles you see on table J. Pb is lower than Mg, so the electrons are going to leave Mg, who's being oxidized. Since Mg is higher, it's being oxidized, lose electrons oxidation. They are going to leave Mg, travel through the wire, and go into Pb, which is gaining electrons reduction. But if we were to attach a battery or power source to this, we can reverse this reaction. We can cause Pb to become oxidized instead. And we can cause Mg to become reduced. So what are the key things to look for in an electrolytic cell? 1. Look for a battery or power source of some kind. 2. No salt bridge. 3. If there's no blurb given, like no paragraph above the short answer question, you're going to flip table J. So that means higher is now reduced for electrolytic only. 4. Red cat and anox still good. Reduction will still occur at the cathode. oxidation will still occur at the anode. All you're doing is flipping what one is getting oxidized and what one is getting reduced. That's all. Everything else is the same. It's just flipping table J. 5, it is not spontaneous. And 6, it creates chemical energy. Aside from that, you're doing nothing different than you've done with the voltaic cell. All it's doing is flipping table J, making it a non-spontaneous chemical reaction that is creating chemical energy. I think that really covers a lot of the big parts of redox. Tomorrow's the last one, people. Hope you guys have a great night. I'll see you tomorrow.